right, so we're ready to start something new now. All right, a lot of what Chapter 7 and actually Chapter 8, when I get back, are going to go over is chemical bonding. So, how are atoms of different elements bonded together, and why are they bonded together that way? So, not only how are the bonds formed, but why do we have different types of bonds for different types of elements? And the first ones we're going to look at, and most of what we're going to look at, is going to require us to be able to kind of draw what we know. So it won't be enough necessarily for us to just say some of these things, but we want to be really as specific as we can be. Just like we did with electron configurations, when we did the arrow drawings, we were trying to be as specific as we could, trying to show what we know about what electrons are doing. And so this is going to be about Lewis dot structures, all right? And so it's just a guy named Lewis. He got to name them, nothing special about that name. But we are going to use his way of drawing atoms and eventually drawing groups of atoms or bonded together atoms or compounds in order to kind of show what we know, all right? So Lewis dot structures, they show the number of valence electrons, all right, in an atom. All right, so valence electrons, again, these are the ones that we just talked about. They're in the highest energy level electrons. You look at the group number, and if you don't have this on your periodic table, please write it, all right, is going to be equal to the valence electrons in an atom, all right? So that's going to help us a lot. So we're going to just go right across a period. We're going to pick the second period. All right, so that's the one that starts out with lithium in it. All right, we're just going to go right across, showing what these Lewis dot structures look like. Because all the ones that are in lithium's group are going to have the same Lewis dot structure. Lithium and sodium will have the same one. Or if you go to group 2A, beryllium and magnesium are going to have the same one, so will calcium. So if we can do one period, then we can do all of them. All right, Lewis dot structures, you start by writing the chemical symbol for the compound. All right, so just like we did here with the Li, remember you want to make sure you capitalize that first letter and lowercase the second one if there are two letters. All right, so Li, and then we're going to literally use dots, all right, just like the name implies, we're going to use dots to represent the number of valence electrons. All right, we know group 1A only has one, so we're just going to draw one dot. All right. If you think of the symbol kind of like it has four sides, so like it's a box, so like we have the top side, we have the right side, the bottom, and the left side, think of putting your dot on one of those sides. All right, it doesn't necessarily have to be where I put it, so I put it on the right side, but pick one of those sides. All right, I'm just going to always do it on the right first because that's just what I like to do. All right, we go next to beryllium. All right, again, think of it like it's a box, all right, and this time you're going to pick two different sides because beryllium has two valence electrons. I'm going to, again, put my first one on the right side, and then I'm going to choose to put my second one on the bottom. It doesn't really matter, though. You could have put it on the top and the left, or the top and the bottom, or the top and the right, however you want to do it, but just two different sides, just not the same side, okay? All right. If we move right across, now we're skipping all those ones in the middle. All right, skipping the transition metals. We're going to go to group 3A, which is boron. All right, group 3A has three valence electrons. So maybe you can guess already, but we're going to pick three different sides to put a dot on. All right, I'm going to go right and bottom, and this time I'm going to go left. Okay, but again, you could pick whatever three sides you want. Once you get to carbon, though, all right, carbon's in group 4A. Carbon only has four valence electrons, which means if we're going to put each dot on a different side, everyone's should look the same for this one. All right, this one we should just have one dot on each side. All right, so there's no kind of alternate way to do that. You just have to put one dot on each side. All right, now that we're finally moving to group 5A, again, this isn't necessarily difficult. There's just kind of a right and a wrong way to do it, all right? Once we get to group 5A, so we get to nitrogen's group, now we're going to start pairing these off, all right? So we start with one dot on each side, all right? So we got our four dots from carbon, All right, but now our fifth one, again, you can choose whichever one you want to pair off. It doesn't matter which one you pair, you just only pair one of them. All right, so I'm going to start on the right again. That's just my personal preference, but it doesn't really matter at all. Okay, so we're pairing off one of them. All right, and hopefully from here now you can kind of see what the pattern's going to be. So oxygen's group, we have 6 valence electrons, so two of these are going to get pairs. All right, and again, doesn't matter which ones, but 2 of them. All right, group 7A, again, we want 1 dot on each side, and then this time, since there are 7 total, we're going to have 3 of them that are paired off. And then once you get to our noble gas, neon, all right, this time, again, there's only one right way to do this. All around it, there have to be pairs. So 4 pairs, 8 total electrons, just like we said in the review. All right, so 8 total valence electrons for neon. And that's going to be the same for all the noble gases except for helium. All right, so just watch out for helium. Okay, this is going to kind of illustrate then, hopefully for you, something called the octet rule. All right, so take a second, pause this video if you need to, write down what the octet rule says. Right, but essentially what it's talking about is says when you're forming compounds, the atoms tend to achieve the electron configuration of a noble gas. All right, so electron configuration here, all right, electron configuration, this just means the same number of electrons, which we already knew because we talked about that in the last chapter. So that just wants the same number of electrons as a noble gas, all right, which in this case usually means 8 because they're in group 8A, all right, unless we're talking about helium. All right, if that hasn't sunk in by now, watch this video a few more times and maybe it will. All right, so usually it's 8 valence electrons. That's why we call it the octet rule. All right, octet stands for 8, oct, like octopus. All right, so that's kind of where that rule comes from. All right, and that's going to be what kind of guides us, again, for all of our chemical bonding, which is what this chapter is beginning to talk about. All right, our first one, ionic compounds. All right, you might already be able to kind of guess where this is heading. All right, but hopefully you're kind of thinking back all the way to chapter 2 when we talked about compounds. All right, so compounds, these are multiple elements, at least 2, but could be more. For us right now, we're going to only focus on 2 at a time, but multiple elements that are chemically bonded together. Okay, so not mixed together. That would be like the air or like just a mixture of elements. That's not what we're talking about. We're talking about chemically bonded together to form something new, so a compound. All right, in an ionic compound then, all right, it's specifically going to be elements that have either lost or gained electrons to form cations, again, which are positive, and anions, which are negative. Okay? One thing that's really key here, though, and again, pause this if you're not able to keep up. One thing that's really important here, all right, even though an ionic compound is made up of things that are positive and things that are negative, anions and cations, all right, overall, okay, overall, it has a neutral charge. It's neutral. That means there's no charge overall. So the positives have to cancel out the negatives. So if you have 3 positive charges, you have to have 3 negative charges that are going to kind of cancel that out. All right, that's going to be really, 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 really important. All right, so remember that. Okay, we're going to see a really easy example now. All right, most common one, sodium chloride. Hopefully you all know what that is. If you don't, it's your everyday table salt. All right, really common ionic compound. All right, its chemical formula is given here for you already. We'll talk about those more later, how you come up with those. All right, but for now, let's just kind of see what this looks like when you form an ionic compound. All right, we're going to use those Lewis dot drawings we just learned about So we're going to look at sodium, Na, and find its group. All right, it's in group 1A. So if you're in group 1A, that means you only have one valence electron. All right, so one dot. All right, chlorine, on the other hand, is in group 7A. So remember, we start out one on each side, okay? And then we pair them up until we get to 7. All right, so notice, chlorine is one dot away from looking like a noble gas, having 8 in its valence shell. And we know that chlorine, the halogens, like to gain 1 electron. All right, sodium's group, on the other hand, remember, they usually have a 1 plus charge, meaning they usually lose this electron. All right, and even though that'll make it look like there aren't any electrons around sodium, we know that underneath that valence shell, there are still 10 more electrons, which will make it look like neon. So it'll look kind of weird maybe. It won't look like it has an octet. It won't look like it has 8 electrons, but we know that there are still 10 more electrons that are under there, including 2 in the first energy level and 8 in the second energy level. All right, so it will still have an octet even if it loses this one. All right, since we know sodium wants to lose this, and we know chlorine wants to gain it, what's going to happen when you form an ionic compound is we're going to see a transfer of electrons. All right, so one that wants to lose is going to give it away to the one that wants to gain. All right, so this again, this is called the electron transfer. All right. Afterwards, all right, what the actual ionic compound looks like after it's made, all right, is sodium. Again, it looks like it doesn't have any valence electrons around it, but we know that there are now a new energy level, that's the valence shell, all right, and we know since it lost 1 electron, it has a 1 plus charge. All right, if you don't remember that, go back to your notes, kind of look at that again. All right, chlorine has a full octet. All right, it now looks like argon, the noble gas, and it gained an electron, so it gets a 1 minus charge, okay? And so then the big question is, what is the ionic bond? What is it that's holding these two ions together, all right? And that's where the laws of attraction come into play. What's holding these two things together is this idea that positives are attracted to negatives. Cations are attracted to anions, right? And that is what an ionic bond is. It's a force of attraction between a cation and an anion, or multiple cations and anions, all right? And so we're going to see some examples that are a little trickier here in just a second, all right? So go ahead, go to the next video so we can practice some more examples together.